we are building a hardware simulator of the Chernobyl reactor control room.
And we created a functional copy of its most important control panel. From here you control an immense nuclear reaction, and from here you trigger the safety systems, of course including the famous SF5. We have received hundreds of comments and messages from you about this project. And so today we will show you all the steps of building it, explain how it works and show it in action. But there is one thing which makes this not just another hardware project. It is this story. During the last decade I visited the Chernobyl Nuclear Power Plant so many times that honestly I lost count. And yet I never stopped being impressed of how large and complex it is. But since 2000, when the last reactor was stopped, it's only a shadow of what was here before. And I vividly remember a conversation with Alexander Novikov. Back then he was the head of the nuclear safety department. He has been there for so long that he even appears as a character in Stalker Call of Pripyat, so many of you actually know him. And back then he told me something like this. Just imagine, it was like a city, 8,000 people working here. Imagine when this gigantic reactor reloading machine was moving, how it felt. And the control rooms, they were constantly full of sounds, teletypes printing, something beeping, gears in the control rod servos making this buzzing sound. It was alive and it was truly incredible. Later I was standing here in our silent control room and I realized something. The stories I share with you about Chernobyl will never be complete if I cannot capture that essence. So I decided to recreate some of the hardware of the control room and then place it on public display. So anyone will be able to experience a small glimpse of that feeling. And logically, we decided to start with the part with which operators worked the most, using which they controlled the actual nuclear reaction. But first we needed to learn, and learn a lot. And so I contacted Andrew Savin, former head of the reactor department of the Chernobyl Nuclear Power Plant. Before that, he was an actual reactor operator of Unit 3. We talked for hours about how each single thing here works. Of course, it's not possible to put all that in just one video or even into a few. So for now I will outline only the very basics before we move to the assembly process. This is Chernobyl Unit 3. Deep below this mosaic floor, inside the active zone, once worked a nuclear reaction of immense power. Try to imagine a very complex three-dimensional wave of particles and their energy, so that's what was happening down there. To control it, operators used control rods and protection rods. They are below all these colorful covers attached to their servo motors. And so by selecting a rod and inserting into the active zone, they could reduce the intensity of the reaction in that place. And vice versa, retracting it would increase it. So now you can probably see it. This control panel is a small schematic model of all of this. But this is a post-disaster version, because after the Chernobyl accident, control systems were heavily modernized. And because of that, this panel is far more complex than the historical one from the infamous Unit 4, which to my mind makes it even more interesting. So, rods are represented by these colorful buttons. Some of them can be selected manually by pushing a button and then moved using this joystick. But some operate completely automatically. But how do operators and automatic systems know where and what has to be changed? After all, you cannot look inside the reactor when it works, right? So around the active zone there are 24 ionization chambers, and they register what the human eye cannot see. On the control panel they are marked with these little white stickers around. In addition, there are detectors that analyze how energy is distributed vertically. They are marked with these white buttons with no inscriptions. Well, you can push them, but nothing will happen. 12 green buttons marked AR and ARM are automatic regulators. Think about them like an autopilot. They regulate the power of the entire reactor and they do it fully automatically. Basically, you set the power level, and if it goes above, AR inserts rods, and if it goes below, vice versa, AR retracts them. You do not press these buttons, they simply indicate which rods belong to these systems. 12 blue buttons marked LAR are local automatic regulators. The principle is the same, but they work in their local areas. Then yellow buttons are USB rods. They are shortened and inserted from the bottom of the reactor. White buttons are manual control rods inserted from the top. Using yellow and white buttons, and in some cases also blue, the operator can finely tune the processes inside. But there are also red buttons, and here we come to so-called AZE. If something goes wrong or there is a need to simply stop the reactor, there are systems of emergency protection, AZE. AZE of the highest, 5th level is triggered by this AZE 5 switch. Yes, before the accident it was a button, but after it was changed to the switch. Then all these rods go inside the active zone within 7 to 8 seconds and then stop the reaction. But a few years after the Chernobyl disaster, an extra safety layer was introduced. It is called BUZZ, which means fast AZE. And if it is triggered, the rods marked with red buttons go inside faster, in just 2.2 to 2.5 seconds. In other words, if AZE 5 is the brakes, then BUZZ is an extra brake for emergencies. Similar to green, these red buttons serve only as indicators, you do not push them. Now, what about these little lights? So, control rods are moved by servos at the top of each rod channel. After modernization, these lights indicate servo malfunctions, but in reality such events almost never happened. So, reactor operators told me that they usually saw this glowing only during indication tests. Well, this is only a brief description, there is much more here and many operational nuances. We will definitely make a separate video about that later, so don't forget to subscribe. And now let's build it. So before all, we need just a few buttons. Specifically 223 of them. Technically, there are a few variations of these buttons, and all of them exist in the power plant control rooms. But the servo selectors specifically are built with this type, P2, P1T. To be sure I had the correct quantity and colors, I positioned everything on my table. Well, it didn't stay untouched for really long. So, original buttons were engraved using pantograph engravers, and then they were painted. So, eventually after quite a long search, we found a contractor who agreed to experiment and try CNC milling. And because of the complex shape of the button caps, they had to become quite creative. So, first they made a reusable matrix where 15 buttons could be secured at once. And then the magic started. And in a few days I received this package, and everything was just fantastic, no distortions, every inscription had crisp edges, just perfect. So next came the painting, and at first I tried to apply paint as accurately as possible. Well, in some cases it worked, in some cases it didn't, but anyway it was a very slow process. So later I discovered a much more effective way. I simply applied massive smears of paint and just let it dry. Then I added a bit of solvent on a folded paper towel. It was quite important to fold it because it had to be soft. And then by moving the button in circles, all excess paint just goes away. All these operations we repeated for 223 times. Next we need the panel itself, so we made it with 2mm steel, just like the original in the reactor control room. Next, I brought the panel to friends who do professional powder coating. I believe you probably know how it looks, but not everyone knows how it is done. So first, the surface is sandblasted or machined almost to a mirror condition. There must be no rust, no oil, no nothing, and then the metal is thoroughly cleaned with solvent. After that, using a special sprinkler, a color powder is applied, and it attaches the surface because of electric charge. Finally, the painted part is baked in a special oven. Well, they could not record that stage because it was very hot, but this is what we got in result. We have a durable, uniform coating. It's actually better than the original, which was likely hand-painted. To be honest, it looked so good that I couldn't resist, so installed just one button just to see how it looks. And still, that was just the beginning, because the buttons are new old stock, never used, but they were stored for years, so everything really oxidized. So first I needed to clean each pin, and we will use 4 of them on each button, and then I needed to cover them with solder. So in total that was more than 2000 operations. Next, to make installation more convenient, I opened each light bulb socket. Because everything on the reactor panel is arranged quite tightly, I have to install the buttons together with servo error indicators. This is what they look like. It is a socket for the indicating light bulb secured using a sleeve, and inside the sleeve you can install a color lens. The problem is that these sockets were stored for so long that the only effective way to remove oxidation was to use a hand grinder. And after that I covered the connections again. Well, it was quite dusty work, but eventually we got a full box of indicators ready to use. And so next, one by one I installed all of that into the panel. The cool feature of these buttons is that they are secured using this metal pod, which makes them hold well on a surface of almost any thickness. The problem, however, is that the nut which holds them in place is not only non-standard in diameter, but requires a special wrench, which of course I didn't have. And so everything was done manually using narrow pliers. At the same time, I immediately placed the color caps, because I had to pay close attention to which button goes what. This is because it appeared that among all buttons there were 3 different designs of the cap lock, and they were incompatible with each other. And all in all, it took me nearly 3 days, but here it is. I have to say, I absolutely love how geometrically well arranged it looks. At this stage I didn't install any rotary switches, because they will obstruct further work, and that's because ahead was this, the wiring. There will be roughly 1 mile of wires and kind of 6000 of connection points. So first I built common power rails for indicators and for buttons, and to make everything accessible they are positioned on different levels. Well, that was a big work. I used both rigid and flexible insulation tubes, cut a few hundred pieces of wire and made these small but durable stands that connect to the common rails. And then, wire by wire, I built this. Well, now it looks like a chocolate cake. Let's add some dressing. So next stage was running more than 400 signal wires for each indicator and from each button. Well, many people told me that this all is extremely complex. But trust me, this is just only a fraction of what is inside the original reactor control panel. Because here we'll use highly integrated digital electronics, and in the real control room everything was built on simpler chips, transistors and discrete logic. In addition, many circuits there are doubled or even tripled for extra safety and redundancy. So our is relatively simple. Also, at this point I decided to use warm white LEDs instead of incandescent light bulbs. This is because each light bulb consumes pretty much current, and if we have hundreds of them working at 27 volts, we'll need a very large power supply, which I find quite unreasonable. And so each wire that comes from the LED has its own current limiting resistor. And after a few days of very intensive work, this is what we have. But we still have 180 something servo error indicators. And at the moment I do not yet have any scenario of using them individually, so eventually I decided to connect all of them except just one to a common power rail. And then just switch them all together using a relay when the indication test is activated. Okay, and now we come to the light bulbs. The problem is, these light bulbs have quite exotic sockets, so this means it's really difficult to find direct LED replacements. And so I decided to make them myself. And so I got a few hundred old and non-functional bulbs, then each one I carefully crushed, then cleaned from inside, and as a result I obtained many empty sockets with two tiny openings. Then I inserted an LED, shaped its pins, one cut, one rolled, and then soldered them. And here it was really good that I tested everything early, because it turned out that inside the buttons the polarity of pins is completely random. Which means that I had to make some LEDs with the anode in the center and some with the cathode in the center. The last step was sanding the LED lens to eliminate the visible dot, and after 223 iterations this is what we got. Lamps for the servo error indicators I made a bit later, because they didn't arrive on time. So let's install one and look. Well, to my mind it looks pretty much like the original. And so after that I placed each LED in a position paying attention to polarity. Now, before we proceed with making a controller for all of that, let's install the missing controls. First go reset buttons of type KE011. They are actually very similar to pre-accident as a 5 button. There are two of them, they mirror each other and now they have a completely different function. They reset the operator's selection. But now I will program one of them to trigger test mode when everything lights up at once. Next we install the joystick, and that's actually a control which is essentially exclusive to Chernobyl Nuclear Power Plant. There is a tiny obscure story, so by the design there should be inconvenient rotary switch here. But operators found it really not usable, so some engineers suggested to place there a telephone key. That's basically a switch like this, it was used in old phone commutators. And it appeared it was a brilliant idea because, like a rotary switch, it can switch many lines, but it also provides a very clear haptic feedback. So my idea that we'll wire it to a controller and measure how long it is held in each position. And with some mathematics that will give us the distance the selected rod travel, which is essential for our simulator. And finally, we need to install 6 rotary switches including AZ5. They are very hard to find and they are highly specialized for energy facilities. We actually had a video a few years ago where we looked inside such switches, so you may remember that they can switch up to 12 lines simultaneously. But we need just one line per switch, so some will be shorter than usual. They come in such boxes. There are MKF type switches that have a latch, and they are used for initiating AZ, buzz and other modes. And there are MKV types, which have several positions with automatic return. They are used to clear AZ and buzz signals. The switches are secured using 4 screws that come in the box. Okay, beautiful, so let's try them. Here goes buzz. And then regulator valve control, well, this one has a very loud latch. AZ5, servo coupling controls, and AZ-SER, AZ-S control, well, all good. And here we have buzzer reset and AZ5 reset. Well, beautiful. So now almost all is assembled, we just need to make it work. Well, here I have to say, now we have massive problems with electricity and you perfectly know why. Well, lately it became quite critical, so a lot of work was done in these conditions. So I'm sorry that some things you will see next were sometimes recorded in half darkness or slightly blurry. Well, I did my best. So, the controller itself will be quite large. I laser cut this long plastic chassis on which we'll place 16 GPIO expanders, 16 LED controllers, a multiplexer and one ESP32 microcontroller. All expanders are I2C and each one can read 16 buttons or 16 switches. But each expander must have its own address, and well, here we have only 3 address bits. That means we cannot place them in one I2C chain, so I arrange them in 2 separate chains of 8, and then I will multiplex them. With LED controllers it is much easier, because they have 6 address bits, so we can place them in one long chain. And that's what the layout looks like. Based on it, I drilled mounting holes and started assembling. First, address jumpers and headers for connecting wires. Then I added ribbon cables between the expanders. With LED controllers I decided to simplify things. I just bent their side headers and soldered them all together, so this is what we have now. A large controller board with convenient access to all headers, and all that runs just on a single ESP32. And now on each of these 400 wires I placed a DuPont connector. Well, at first I didn't have a proper crimper, so about half of them I made using pliers. Surprisingly, it works quite well, just not very fast. A bit later I got a proper tool and things became much faster. And this is what we got. All common positive and negative rails are connected to this additional board. Here we also have a relay that switches on all servo indicators at once during test mode. And we also have an RS-232 interface port. To this port we'll connect a dot matrix printer, which logs every operation. The last wiring stage is connecting the rotary switches. Well, I was worried about signal interference, but eventually I simply made one long shared signal line connected to one of the expanders. And fast forward, everything worked just well. Once all that was finished, the last missing components arrived. That were light bulbs and colorful lens caps for the servo error indicators. I made LED versions in the same way as those for the buttons. I removed the original bulbs and attached LEDs, but this time with an additional separator. Well, just saying there are industrial LED versions of these bulbs, but honestly they do not glow as nicely as ones I made. And once each lamp was ready, came a moment I've been waiting for a very long time, installing those beautiful glass lenses. They are called L1, and it's actually quite hard to find them on sale in such quantity, so that was kind of another small quest. Well, from what I can see, in the real control room there are red lenses over red and yellow buttons, then green lenses over green and blue, and the rest are white. So this is what I followed, and if needed it will be easy to change later. Beautiful. Now we add a few finishing touches, specifically covers and labels for AZ5 and other switches. These covers were handmade from thin strips of stainless steel, so using scissors I cut the main shapes. Next I attached mounts which I made using a bolt cutter, and that's what we got. Then I made 4 additional parts for upper sections. The purpose of these covers is to prevent accidental triggering, so they do not block the switch completely. But considering how much force is needed to turn them, that actually does not change much. Next, we need the labels, and on the original panels these labels were made using famous Taché 3 stencils. So these are such sets with plastic sheets and cut out letters. You place the stencil and then apply half-dry paint or a crayon. I took original period paper and first tried some paint. Well, I didn't really like the result. And so instead I used a red crayon, and to be honest it felt a bit nostalgic. Because the last time I used such stencils was maybe 25 years ago. Later everything just moved to printers. And back in the 90s we could not even imagine that one day this will become a fashionable retro design technique. So eventually this is what we got. I attached the labels using the double-sided adhesive tape. But with the SZ5 cover it is more tricky, because the font there is non-standard. It looks to me that it was applied using a handmade stencil and paint, so eventually, out of options, I made the stencil and painted it myself. Once everything was ready, I positioned the covers and secured them by bending the mounts. All these covers must also have a plasticine seal, but before I made them, I had to place labels for positions and systems. So this I ordered to be printed on plastic and laser cut. I also secured them using adhesive tape. And after that, I could add wires and the seals. Back in the day it was a typical way to seal such controls, because inside the plasticine a metal seal was pressed. And so if a cover was opened, the wire would just break the seal. Simple and effective. And now it is done. And I honestly cannot express how huge this thing is. Alright, let's finally test it. So, when the power is applied, the system runs a self-test. All lights blink for a moment and the printer will get a message. Every operation performed on the panel is recorded in memory and logged. In addition, this system has its own Wi-Fi hotspot for debugging. And so if I connect to it using Telnet, I will see the same log that the printer produces. For example, I select several control rods. Their buttons light up and I immediately get a message showing which rods are selected and to which pins of the controller they belong. Later we can easily change these messages to look exactly like those produced by the Scala computer. Now I press reset and the rods are deselected. Now let's try to move some rods, so I select a few rods and move the joystick. And immediately we get a message that the selected rods left their upper limit switches. Now when I release the joystick I get another message showing which position they reached. In a real control room this information would appear on a large self-send display. And finally let's try the test mode, so I press this button and all indicators turn on and blink. You can actually hear relay clicking.
And we added one little Easter egg. So here between buzz and AZ5 there is this switch which normally permits opening a certain valve. And it normally has just 2 positions, on and off. But we added a 3rd position which is unmarked, and now look what happens. Now, what are our plans for our next steps? So first we're going to add a block of devices which are related to automatic regulators. We reviewed some of them before on our channel, so they will actually show some of these things in operation. what is even more important, we are going to implement here more realistic configuration of fuel rods, control rods and protection rods, because that will allow us to more simulate operation of the automatic regulators, local automatic regulators and other systems. Because right now everything here is basically undefined, and if I, for example, turn the SFI